Hey, we're going to introduce some derivative rules, but first let's make sure we know the old notation. These rules are going to make life a lot simpler. But the notation we're familiar with so far is that if we're given a function and called it f of x, we could denote the respective derivative as f prime of x, or if we called it y, we'd denote the derivative as y prime. Okay? So that gives us a link between a function and its derivative. And another common notation we have is kind of like a function definition. It's this d over dx. Basically, that's a change in the function, which is a change in the y over the change in the x. So that's where we get the slope from, change in y over change in x. But we see the d over dx, and then there's a function inside here. And then however we work it out, the derivative would be the result of that. So we're going to use that notation down below to go through some rules, and we'll present the rules first. So the first rule, the constant rule here, the derivative of a constant is 0. Now this is if the constant is all by itself. We'll just have to get used to how constants operate, but you may think that back to when we just add 5 to the end of something, it might move it up or down. It really doesn't change the shape, it just changed the location. So constant added or subtracted to the end of something does not change the slope. So the derivative of a number all by itself is 0. The next rule is the power rule. The derivative of x to the n, so a variable raised to a power. This becomes, the power comes out front as a multiplier, n times x to the n minus 1. So we bring the we bring the power out front, and then we reduce the power by 1. And we can do that with any type of power as far as a number. So it could be a fraction or it could be negative. It just can't be 0. It doesn't make any sense there. And then we get to stuff that's a little bit more general, constant multiplier rule. So if we know how to take the derivative of a function and it's multiplied by a constant, then that constant or that coefficient just stays there. And we'll see an example of that soon. The sum difference rule, basically if I've got two functions added or subtracted together that I can handle, I can take the derivative of them separately and have them added or subtracted together. So let's see how that works out with some examples here. So the first thing I've got here, I'm going to try and take the derivative of x squared plus 6. So with the x squared, what I'm going to do is I'm going to apply that power rule. Okay, so the 2, pause. So the exponent of 2 comes out front, and then it'll be x to the 2 minus 1. So this is the power rule that you saw up above. So in that case, the n was 2. Okay, so this is what I'm applying here. We're going to clean that up in a little bit. And then separately, the 6, where it says plus 6, that goes to 0. So it'll be plus 0, and that's the constant rule. Okay, and what you should realize there is that we had two things added together. So basically, we did a sum or difference rule here. So we knew how to take the derivative of x squared. We have a rule for that. We have a derivative for a constant, so adding them together, we can do them on their own. So this gives me just the result of 2x for the derivative. Okay, so if the function f was x squared plus 6, the derivative would be 2x. And that should have come about as far as the long limit definition. We should have used that in some place. Okay. The next one down here, we're going to take the derivative of 9x cubed plus 5x minus 6. So with the 9x cubed, we're going to use the power rule. Okay, so first of all, there's a 9 in front of it. So the 9 will stay there. That's the constant multiplier rule. And then the x cubed, the 3 will come out front, and the exponent will be reduced by 1. So right here, the 3x squared as it'll be, that will be the power rule. Can't spell. But the bigger picture there with the 9 in front of it is the constant multiplier. And it's getting really meaningless down here. Just trying to make sure everything is seen there. Okay, so that's how those related to each other. Then we got the 5x. So when we pull the 5x over, it'll be 5 times, right now it's an exponent of 1, so the 1 can come out front and it'll be raised to the 1 minus 1, which will be 0. But once again, this is the same thing. It's a power rule and it's a constant multiplier rule. Okay, and we're using the sum or difference rule all the way across. And then the 6 goes to 0. Okay, so as we clean this up, the derivative will be, it looks like 27x squared plus 5, because that'll be x to the 0, and anything to the 0 power is 1. Let me write that a little bit neater. Okay, next we have the derivative of 9x to the negative 3 minus 6x. So again, let's try this out. We're going to keep the 9 because it's a constant multiplier. The negative 3 will come out front, and then we'll have x to the negative 3 minus 1. Okay, so we got a power rule and a constant multiplier rule there, and just because it's negative doesn't mean anything different as far as the exponent. We're still decreasing it by 1. And then the negative 6x, the negative 6 stays there as a coefficient. It's x to the first, so the 1 comes out front, and it'll be x to the 1 minus 1. Okay. Now that cleans up rather nicely. In the end, we will have negative 27x to the negative 4. So remember, we're subtracting 1. So the exponent goes down, even if that's further away from 0. And then we'll have minus 6. Okay. The last example I have right here is 3x to the 5th plus 4x to the 3/2 minus 5x to the negative 2 plus 7. So 3x to the 5th, let's slide down just a little bit. 3x to the 5th will be 3 times 5x to the 5 minus 1. We'll clean it up in just a second. Plus 4x to the 3/2, so the 4 will go there. The 3/2 exponent comes out front, and then the 3/2 will be decreased by 1, so we'll have to do a little bit of fraction work there. And then the minus 5x to the negative 2. So the negative 5 will be the coefficient that stays. The negative 2 will come out front, and it'll be x to the negative 2 minus 1. And then the 7, the nice little 7, will just go to 0. Okay. So basically what you should be getting out of this is the power rule and the constant multiplier rule. So in all these cases, what we've done is we've left the coefficient in front of the term. We've brought the exponent out front as a multiplier and reduced the exponent. So we get 15x to the 4th plus, it looks like 6x to the 1/2. Do a little bit of fraction work there. Plus 10x to the negative 3rd. It takes a little bit getting used to, but it's not hard, and most people pick it up pretty quick. What you see here is all these things are items we could have done with the long limit definition, but they would have been a lot of work. So here, this rule is just a shortcut to get us what we want. All right.